this last lecture? It was the It was
So
the
I think
same
I
as the
talked about it in
category.
the case where K is algebraically closed.
Oh,
I don't think I
shoot.
talked about it in general. Yeah, so in the case where K is algebraically closed, it's just the category of, well, of abelian groups if we're talking about abelian shapes. Yeah. So can anyone explain to me how to do this for a general field? So Arvin has a suggestion. So he suggests the category of G modules, where I guess G is the Galois group. So let's set G. So let's set G to be the Galois group of K sep over K. Right. Yeah. So here we have to choose a separable closure. Ks of K. Sorry, what were you saying, Ali? I think I interrupted you.
No. I was just guessing maybe we should use like one of the descent stuff we were talking about, but it's probably
yeah, that's correct. Yeah, so I claim there's an equivalence of categories as follows. So the claim is that that there's a natural functor from sheaves on the Etale side of spec K, Etale, to the category of discrete G modules. So what do I mean by discrete G modules? I mean G is a topological group. It's given the inverse limit topology, and I mean like modules with the discrete topology with a G action on them, so the G action is continuous. So in particular, the action on any element of such a module factors through a finite quotient of G. So typically, when you think about Galois representations, like you might think of a representation into GLN ZL. So that's not an example of such a thing. But if you take a Galois representation into like a finite abelian group, that is a discrete G module. Okay, can anyone construct this functor to me for me? So the claim is that there's a functor. I'm sorry?
Can you give an example? Because I've never actually seen one. An example of an indiscrete G module? Of
an indiscrete or a discrete one?
Indiscrete one.
Oh, sure. If you take the Tate module of an elliptic curve, so that's ZL squared, and the Galois action on it is not continuous for the discrete topology, but it is continuous in the L-adic topology.
But isn't every point stabilized by some
So maybe you're thinking of the torsion itself, but the Tate module is not the torsion; it's the inverse limit.
Oh, I see.
Okay, cool. Yeah. So at each finite level, you have a discrete thing, but if you have an inverse limit of discrete things, it's not discrete anymore. Okay, and Benjamin has told us the formula. So what do we send? We send f to the colimit, so the direct limit over here K is contained in L is contained in our choice of K sep of f of spec L. So this is, you're supposed to think you're evaluating f on the separable closure. That's not something that makes sense because the separable closure of a field is not locally finitely presented as an extension of that field. So it's not actually in spec K at all, but here we're taking the direct limit over all intermediate subfields. Okay, so the claim is that this is a discrete G module. And that's because at each finite level, you have a discrete G module, so you should convince yourself of that, and then a direct limit of discrete G modules is a discrete module. And the claim is that this is an equivalence of categories. Okay. So as a corollary of this claim, we can actually describe Etale cohomology for spec K. So can anyone help me out? So what is the description? So maybe let me call this functor iota or something. So the corollary of this of this statement is that the Etale cohomology of spec K, Etale, with coefficients in some F is the same as the Galois cohomology. So the group cohomology of G with coefficients in iota of F. So why is that? Well, derived functor cohomology only depends on the ambient abelian category. So if we have these two ambient abelian categories, as long as we know that H0 is the same, then we win. Okay, and what's H0? Well, I would have to tell you the functor going back. So let me tell you the functor going back. So the functor going back is that you send a discrete G module M to the fixed point. Well, let me kind of sketch the proof of the claim. So proof of claim. So what's the inverse functor? Can anyone tell me? I kind of started saying it, but I'm curious to know if anyone sees it. Okay, so first of all, maybe let's say why is there Galois action here at all? It's because Galois acts on the diagram of intermediate subfields here. So it acts on the whole diagram that we're taking direct limit of. So that's why we get a G module, and then you should check it's a discrete G module. So what's the inverse functor? So given V to spec K, an Etale map, we can write V is the disjoint union of some spec K primes, where here K prime over K is finite separable. So this is the classification of Etale K algebras. And then how do we so now given a discrete G module, a discrete G module M, we send M to the following sheaf. It sends V to the product of the fixed points of the absolute Galois group of KS, of K prime. Here. All right. So this is the inverse functor. You should check that this is an inverse functor. It follows from Galois descent. Oh, and I see Benjamin was, yeah. So Benjamin explained how to do this on connected things, and then yeah. So this is the general formula. So that's exactly right. Thank you, Benjamin. Sorry, I missed that in chat. Okay, and now what this is telling us is that so proof of the corollary. And once you check that this is actually an inverse functor, it's telling us that the global sections on spec K of F, spec K of F are just the same as well, that's the same as taking sorry, I thought someone said they couldn't hear me. Of taking this sheaf iota F and then taking the G invariance. Okay, so what that says is that H0 goes under this equivalence I to invariance. And this implies by the formalism of derived functors that Etale cohomology, well, it's the derived functors of taking invariance, so it's group cohomology. Okay, and maybe it's worth remarking, I mean, the fact that we're working with discrete G modules here is really important. Like normally when you think about Galois cohomology, like with for example, with coefficients in the Tate module of an elliptic curve, as in the example we were discussing with Arvin, you're working with continuous group cohomology. And that's it's like a more subtle thing. It's not actually a derived functor. But here, because we're only thinking about discrete G modules, this is like a legitimate proof. All right, are there any questions about that?
Is this related to the thing like we were talking about earlier of how we don't like take the p-adic constant sheaf when we're doing Etale cohomology?
It's exactly the same issue. Yeah. So you could ask like, I think early on, so right now we're only talking about like honest Etale cohomology of things like Z mod L to the N. And the goal when we try to prove the Weil conjectures will be to use things like ZL. Like you want, like when we're trying to take, like we're trying to count some number and we want to do that by counting some traces. And if those traces live in a ring which it doesn't have, in which some prime is 0 or some integer is 0, that won't actually tell us the number of points. It'll just tell us congruences for the number of points. So in the end, when we define L-adic cohomology, we're going to take some inverse limit. And you could ask, like, why not just use like the constant sheaf ZL? And it's exactly the same issue. It'll give you, like, because you're not using the topology on ZL when you make these definitions, it would give the wrong answer. So there are ways of getting around this, which I think I mentioned. Yeah, so Arvind asks, can you give the example for the inverse functor where M is EK bar for an elliptic curve? Sure, yeah, that's a good example. Yeah, so let's just do an example of this functor from discrete G modules.
Also, I think your screen is frozen.
To sheaves on spec K et al. So if I understand your question is, well, let's maybe go both ways. So if I understand your question is, so suppose we start with the sheaf Hom into some elliptic curve.
Excuse me, the screen is frozen?
Is that right? And you want to know what happens? Yeah, they are frozen. Let me start sharing again. Can you guys see this? Or
no, I don't see anything.
Square? Hello?
Yeah, we can't see anything. It's just a black square.
Just blackness. Oh no. Okay, let me try some stuff. Okay, again, a black square. That is weird. I've lost audio.
Can you hear me?
No, we can hear you fine. But...
Shoot. Okay, let me try some stuff. Yeah, I can't hear you. Oh. Did that fix it?
It's back. Can you hear us?
Yeah, and can you see me moving around?
Yeah.
Yes.
There was apparently a problem with my headphones. Weird. Sorry about that. Okay. So you guys, was this the question, Arvind? You wanted to understand what happens when we look at maps into an elliptic curve?
No, I thought you can take your discrete G module to be E of K sep.
Oh, I see. Yeah. So it's the same example. So yeah. So here's a discrete G module, as you said, and I claim this goes to the functor Hom into the elliptic curve. Do you see why that is, Arvind?
Yeah, like L points, right?
I'm sorry?
L points, right?
Yeah, exactly. That's right. So the point is that an L point of the elliptic curve is exactly the same as a Galois invariant K-set point. Agreed?
Sure.
Okay, cool. So that's the reason. Great. Okay, so are there any questions about that before I start talking about how to, like, in principle, compute Etale cohomology? All right, assuming my audio is still working, I guess not. So okay, so how do we compute cohomology, like in real life? Like, there's a more computable version of cohomology, and that's called Czech cohomology. So I want to introduce Čech cohomology in this setting. Should we take a 3-minute break before I do that? Since we're about halfway through. Does anyone have a preference? I guess we kind of took a break when my technology quit. All right, let's take maybe a 30-second break then, and then since people are not expressing a preference, and then we'll return.
Sorry if I'm being annoying, but I'm just sort of stuck on this thing that I'm worried about, which is if you. So I mean, is it true that the L points are characterized by the fact that they're exactly the k bar over L invariants or k sub over L?
Over L invariants, yeah. Yeah. So what worries you about that?
I'm not sure.
Imagine your elliptic curve is like a cubic in P2. And so you're looking for, what are you looking for? You're looking for solutions to that cubic in L, right?
Right. I guess you don't need them. So it's okay if actually what you get by taking invariances lives in a proper subfield. So that doesn't actually.
Yeah. That can happen, and that's okay. That's still an
right, and that doesn't contradict. Okay, that's cool.
Yeah. That's a good question. Okay, I guess break over. Okay, so I'm going to start talking about Čech cohomology. So there's 2 warnings I want to give. So warning 1 is that in general, Čech cohomology does not always compute. So Čech cohomology does not always compute. Compute Etale cohomology. I mean, this already happens like for sheaf cohomology on very bad topological spaces. Like it's not always true that Čech cohomology computes derived like sheaf cohomology. But it's also not true. There are counterexamples for Etale cohomology of schemes. So for example, I think if you take A2 with a doubled origin, that gives you a counterexample. Okay, and 2 is that it's not really computable. So Čech cohomology is not actually computable, but it's still going to be useful for theoretical reasons. Okay, so let me say a word about why Čech cohomology in the Etale setting is not actually computable. So how do we compute Čech cohomology? Like when does a Čech complex like actually compute sheaf cohomology? It's like if you can find a cover of your original space, so that for each object, like object in your cover, and for each multiple intersection, the derived functor cohomology of your sheaf vanishes. Right, that's sort of the condition for when Čech cohomology computes Etale cohomology. But now, like, imagine you have an algebraic curve, and think of it maybe just as an open subset of a Riemann surface or something like that. Like, there's no Etale maps to that thing typically from algebraic curves, which have that property. Like if you take any Zariski open subset of an algebraic curve, like just thinking over the complex numbers, it has lots of interesting cohomology. So somehow the point is that you can never actually find an acyclic cover, and that this so maybe let me write that. So it's because in general, acyclic covers do not exist. So this is one of the big differences between sort of Etale cohomology and, let's say, singular cohomology of manifolds, and it makes things a lot harder. So another way of saying this, by the way, which I think is I found very revealing, is so when you find an acyclic cover, what you're usually looking for is something like a cover by contractible things, and so that the double intersections and triple intersections and so on are also contractible. Like that's the usual situation with manifolds, and that's not so hard. And the reason why is just that manifolds themselves are locally contractible. So in general, it's not true that schemes are locally acyclic in any reasonable sense. What is true, and I'm maybe we'll discuss this as an advanced topic near the end of the semester, is that schemes are locally k pi 1s. So somehow Etale cohomology you can actually compute in terms of group cohomology. And that, in my view, is really cool. And it's something that is due to Arden, I think, but it's been very fruitful. So this point of view is something I learned from Peter Schulze. Cool. Okay, so with that, are there any questions before I actually define Czech cohomology? So Benjamin Church says, is it still true that any fixed cohomology class, there is a cover on which this class is 0? Yes, that's true. And then Sarah asks, is there a natural topology that's fine enough that you get things like acyclic covers? I think the answer is no, but I don't actually, maybe the answer is that I don't know of such a topology. Yeah. I mean, okay, like you can take the discrete topology, like where every morphism is a cover, and I think that will work, but like maybe you mean, is there a natural topology where cohomology is still an interesting object? And I don't know of such a thing. Yeah, that's a good question. Are there any other questions before I move on? Okay, so let's say we're in the following situation. So let's suppose we have U, which is the union of some UI to X. So this is equal. I suppose this is an Etale cover. So if Nicholas was here, he would probably complain that this union may only be locally finitely presented and not finitely presented, and I will avoid that by saying that I am working in what I originally called the Etale site, so with locally finitely presented things. And so suppose I have some sheafs, some abelian sheaf F, which is a sheaf on X Etale. Okay, so from this U, we get some diagram, which probably is familiar from when we talked about descent. So U maps to X, and then there are two maps from U cross U over X to U, so the two projections. And then there are three maps from U cross U over X to U cross U, so the projections onto the first, second, third, and first and third factors. And then so on. Now there are four projections from the four tuple product over X. So what are you supposed to think about this diagram? You're supposed to think U is some cover. These are the double intersections. These are the triple intersections. And there are quadruple intersections, and so on and so forth. Okay. So note that it's not literally that, right? So for example, unless you're allowed to intersect and open with itself. So for example, like UI cross UI over X lives in here. So kind of the intersection of something with itself. Okay, so now given our sheaf, we can apply our sheaf F to this diagram, and we get a diagram going the other way. So we get F of U, F of U cross U over X, and I've deleted note that I've deleted F of X here. Okay, so this is I guess a co-simplicial diagram of abelian groups. It doesn't really matter if you know what that means. It's just a diagram with a lot of maps. And given a diagram like this, you can make a chain complex. And how do you do that? Well, you just take the alternating sum of these maps. So this is like D1 and D2, or maybe D0 and D1, and so on. And this gives you a chain complex, which I'll write. So this is the Czech complex. So I'll call this C U over X F, I think is the notation I'm using. And this is just the chain complex 0 to F of U to F of U cross U over X to so on, where these differentials are the alternating sums of these maps above. So this is called the Czech complex. Maybe it's worth remarking. So there's unusual topological spaces. There's two notions of the Czech complex. So there's this one, which is sort of the big Czech complex. And then there's also the so-called alternating Czech complex, where you throw away things like U intersect itself.
And you can't do that in this setting because like U intersect itself, like U cross U over X or UI cross UI over X can be an interesting object, right? Like it's not necessarily a section, for example, from U cross U over UI cross UI over X to from UI to UI cross UI over X. Like for example, U could just be a single finite Etale cover of X. Okay, and then sorry, I should put a little hat here to say that check. And then given this, so then we're going to define the sort of total Čech complex. So this is the Čech complex of the Etale site with coefficients in F. This is the direct limit over all covering families. Covering family of these sort of Čech complexes relative to the covering family. Okay, so this is Čech cohomology. Are there any questions about this? All right, so let's talk about this. So the first proposition is that H0, oh yeah, maybe let me make one more definition. So then the definition is that Čech cohomology, so HI of, with this little hat thing, U over XF is just going to be HI of the Čech complex. And then also we can define Čech cohomology of the whole site. So this is defined to be the cohomology of the total Čech complex. Right. Okay, so what can we say about this? So the first statement is that the zeroth Čech cohomology is equal to, well, it doesn't depend on the cover.
So, sorry, a quick question. I think this may be my first time seeing direct limits of chain complexes.
Oh, it just means termwise.
Okay, cool.
And Benjamin Church asks, are we assuming covers are finite? No, we're not. Why do you ask? It's a good question. So this is something I alluded to is, so is the question, why am I allowed to take this union, maybe? Yeah, so that's a good question. Yeah, so there's two issues. So one is can I take the direct limit? Okay, so Peter asked, is it the same if we take the cohomology first and take the direct limit? It is. That's just because taking direct limits is exact. So the question is, what can we do if this is not quasi-compact? Yeah, so there's an issue in taking direct limit in principle. So this is one of these issues where one of these cases where there's set theoretic issues. So if you ignore the set theoretic issues or choose a universe, then everything I'm saying is fine. These are still locally finitely presented. So I think I mumbled something about local finite presentation when I mentioned this union. Otherwise you have to limit yourself, not necessarily to finite unions, but how should I say this? But yeah, you should assume X is quasi-compact and then limit yourself to finitely presented things. Yeah, so you have to make some choice about how to do this, and yeah, so one way to do this is to only work in the finitely presented setting. And then Benjamin Church says, I'm not clear if our definition of Etale includes quasi-compact, and it doesn't. So it was just locally finitely presented. So it does not actually include quasi-compact. But you're right that there are actually issues with this limit if we don't include it. Yeah. Yeah. If you want. Yeah. So there's two choices you can make here, and maybe I should actually make one rather than always talking about two choices. So one is to just limit ourselves to the case of finitely presented things. And Benjamin asks, for descent, do we need quasi-compact? So the answer is yes, but if X is quasi-compact, you can always refine a cover to one which is quasi-compact. Yeah, so maybe the easiest thing to do is let me actually work with what I called, so let me work with, so here I'm going to work with X Etale finitely presented even. So this is a subcategory of XFPPF. But yeah, so this is the presentation choice, and like I claim whatever choice you make, the answer will be the same, but maybe it's best to actually work with a choice. So I'm going to work with finitely presented things for now. Okay, so the claim is that these two things are equal, and moreover, they're equal to the usual H0. Okay, so can anyone tell me why this is true?
Because F is a sheaf.
Yeah, so this is exactly the sheaf condition. So the proof is that we're saying that f of x to f of u to f of u cross u over x is exact, but this is the sheaf condition. Okay, and then that gives us that the first term here is isomorphic is equal to the last term. And then the middle term is the direct limit of the kernel of the sequence, and direct limits are exact. Cool. Okay. So let's do the next proposition. So the next proposition is that the Čech cohomology u over x I is isomorphic to the Čech cohomology of x Etale I is 0 if I is positive and I is an injective object. So let's actually prove this. I'm gonna give you a different description of Čech cohomology in order to do this, which I think is kind of cool. So I think this is kind of a useful point of view. Oops. So it's enough to show that that this complex for any cover U is exact away from 0. Can anyone tell me why this is true? Well, why is it true? Well, that this is literally the statement of the first equality, and then the second one is the direct limit of this statement. Okay. So here's the cool idea. I really like this. So I'm going to let z sub u be just the kind of free abelian group on the following functor. So ham over x into u. Okay, so what do I mean by this? I mean that if I evaluate this on a X scheme V, I take the set of maps from V into U over X, and I take the free abelian group on that. Okay, then the claim is that we can rewrite the Čech complex as follows. It's the same as the following. So we have ham zu into I, going to ham of z u cross u over x into I, going to ham of z u cross u cross u x into I, and so on. Can anyone tell me why this is true? So, oh, by the way, so what are here we're taking, what are we doing? We have this complex. This is a complex of sheaves on the Etale side of X. Sorry, so what is this map? I mean, here we're taking these functors into u to the I. So these are contravariant functors. These functors themselves form a simplicial diagram because the u to the I over x do. So Hom into them forms a cosimplicial diagram, and we're taking the free abelian group on that, and that's where this complex comes from. Okay, and then this, how are we getting this complex? We're applying Hom into I.
Is this just Ionetta's lemma?
Yeah, it's just, yeah, that's exactly right. It's basically the Ionetta's lemma. Yeah, so okay, so you can also just check by hand, like these two complexes are isomorphic. Okay, now 2, I claim it's enough to show that this complex ZU to ZU, there's a natural map Z to ZU, just the inclusion of like constant maps into ZU. This goes to ZU cross U over X and so on. So the claim is that it's enough to show that this is exact. Can anyone tell me why that is?
Because homing with an injective is exact. Oh,
yeah, that's right. And Sophia's does the same thing. Homing into an injective is exact. So we want to show that this is exact away from 0, where we just get global sections of I, which is Hom Z into I. So okay, it's enough to show that this is exact. Okay, and then the three is actually, well, this is actually the following. It's a special case of the following fact. This is a special case of, well, let's let S be a set. We can make a complex as follows. So we take the free abelian group on S. So Z includes into this just via the sort of constant map set of S. This goes to Z of S cross S. This goes to Z of S cross X, S cross X, S cross S, and so on and so forth. Okay, and this is always exact for any set S. Does anyone know what the proof of this is? It's very closely related to something we did when we did descent. Sorry, and here maybe I should write this slide. I mean, it's not quite the free abelian group. It's maps from this into Z. Maybe that's probably the better way to write this. Yeah. Otherwise, there's issues if S is not finite. Okay, so the proof, it's actually just the same as the proof that of the Amundsen complex being exact that we did in faithfully to flat descent. So you base change. So you tensor with Z adjoint S. This is a flat Z module, or yeah. So we can do that, and then there's a null homotopy. It's a flat Z module with supported everywhere on Z. So we can check exactness after making this base change, and then we do the exact same null homotopy as last time. Okay, so you should check this as an exercise. Okay. So this completes the proof. So what do we know? We know that Czech cohomology agrees with H0 here, and it agrees with derived functor cohomology on injectives. So what else do we need to check that Czech cohomology is isomorphic to derived functor cohomology? So, or, I mean, I told you it's not isomorphic. So what would we need to check? So there's one more thing we would need to check to show that Čech cohomology is isomorphic to derived functor cohomology.
Well, at the moment, we don't even know that different covers give you the same homology, I guess, right?
I'm sorry?
Because this depends on the cover, right?
Sorry, when I say Čech cohomology equals derived functor cohomology, I mean.
Oh, you mean the limit, I see.
The direct limit.
I see.
Yeah, so you're right. In general, I mean, for a given U, it will Čech cohomology will basically never compute derived functor cohomology. So we already said they have the same H0, Sarah. So we need one more thing. So the theorem is that, and this is a sort of general theorem about Čech cohomology and derived functor cohomology, that if for all short exact sequences of sheaves, so 0 to F1 to F2 to F3 to 0 in sheaves on X Etale, then the induced sequence 0 to the Čech complexes of these things. So F2, the sort of direct limit Čech complex of F3, 0 is exact. So if this is the case, then we get a long exact sequence in Čech cohomology, right? Just using the snake lemma. So if this is true, then there's canonical isomorphism between Čech cohomology and derived functor cohomology for all F, for all I and all F. Okay, and the proof of this is basically the theory of universal delta functors. So the point is that a derived functor is determined uniquely by H0. The fact that it's right derived functors are determined uniquely by their H0, what they do to injectives, namely their higher right derived functors applied to an injective give you 0, and the fact that they have a long exact sequence associated with short exact sequence, which is functorial. So given this condition, this exactness, we win because we get that last statement, that delta. Okay, and the problem is that this sequence of complexes is not in general exact. So it's always left exact. That's not too hard to see. It's not always right exact. Okay, and the theorem, which I won't actually prove, but if you want to read it, you can look in Milne section 3. And I'll kind of sketch, I'll give you a lot of consequences of this. So the consequences is that this is true if X is quasi-compact, and if any finite subset of X is contained in an affine. And can anyone give me an example of like a checkable condition for when the hypotheses of this theorem are true? So the main way I know how to check this weird condition about every finite subset.
Quasi-projective?
Yeah, so quasi-projective is the example. Okay, and Benjamin asks, why is Čech a universal delta functor? And the reason why, so what do I have to do? I have to make the boundary maps in a long exact sequence. And well, here if I have to do it in a functorial way, well, what are the boundary maps? They just come from the long exact sequence associated to checking HI of this. Why is it a universal delta functor? I see. Yeah, it more or less follows from the, yeah, how should I say this? Oh, I see. I think I actually have not, unfortunately, given you the complete proof. Yeah. So maybe we'll see this next time. Well, it's 0 on injectives, so we just proved that. But we're out of time. So maybe we'll see this. I'll say we'll see this next time. using the check to derive special sequence. Using check to derive special sequence. So basically, I just need to give you a morphism from derived functor cohomology to Čech cohomology, and we'll see that. Well, we're out of time. Thank you all for coming. And hopefully next week, we're going to get to some actual computations. So I'm going to finish up this Čech stuff, and then we'll compute Čech cohomology, or Etale cohomology of curves. So I'll stick around for a few minutes if anyone has any questions. Thank you, Sophia and Mencelos. Any questions, Ollie, Jose, and Benjamin? Yeah, so I have to make the map the other way, and at least one way to do it, Benjamin, is to use the Čech to derive spectral sequence. Yeah, that's exactly right. So the main issue is that it's not in general right exact. Yeah, did I show it can be effaced? Let me think about that. See you, Jose. Ah, yeah, that's right. Yeah, I guess as soon as you know it's kills injectives, then I think you win, Benjamin. I have to think about it a little bit. I mean, that's more or less the proof I have in mind for using Čech to derive. So the point is, so do you know what I mean by the Čech to derive spectral sequence? Yeah, okay. So we'll see it next time. I mean, yeah, and it'll give you a map going the other way, which is more or less what you need. All right. Thank you guys for coming. Let me stop recording here.
Thanks.